Hello, Assalamualaikum. So we are going to continue chapter 3, which is continuous time and discrete time Fourier series. So let's look at what we are going to learn for this chapter 3. So the first one will be on continuous time Fourier series. Second part will be on discrete time Fourier series, and lastly will be on property of continuous time and discrete time Fourier series. So let's just do a recap on the chapter 2. So what you have learned in chapter 2 is on the representation of LTI system, with which is you may represent the system as a linear combination of shift and impulse. So the method is that you learn to do convolution, which is there are two types, which is convolution sum and convolution integral. So convolution sum is for the discrete time signal, and for convolution integral is for the continuous time signal. Okay, so so now for chapter 3 is that we are going to go for using Fourier series, so which is an alternative representation for this continuous time and discrete time period signal. Which is, first one is that you're going to do you're going to use the trigonometry method, and second one is using the complex exponential method. And in comparison is that in chapter 4 you're going to learn to actually represent the signal using Fourier transform. So it's actually a representative of the signal in discrete time and continuous time for a periodic signal. So the difference is that, if you see here, is that for Fourier series is that you're going to represent it for periodic signal, and for Fourier transform is for aperiodic signals. Okay, so both chapter 3 and 4 is going to use the method of linear combination of complex exponential. So let's go to the introduction of Fourier series. So Fourier series is to discover that a non-sinusoidal periodic function can be expressed as an infinite sum of sinusoidal function. So meaning that according to the Fourier theorem, any practical periodic function of frequency omega naught can be expressed as an infinite sum of sine wave and cosine function that are integral multiple of omega naught. So therefore, so let's just go to watch this video to look at what is actually Fourier series, definition of Fourier series in a general term. Okay, so based on the video that you watched just now, so let's just do a recap. So recap is that on the exponential and sinusoidal signal. So in the video, you may see that they actually discuss about the signal which is you have a complex signal. So example is that you have cosine theta plus j sine theta. So you have a complex signal here. So it's equal to e j theta. So this one, this definition how you get this value of Euler relationship is already discussed in chapter 2 before. Okay, and from here, from this equation is that you are going to actually write out the equation in polar form. So sigma plus j omega will be equal to r cos theta j r sin theta, which is in polar form. Okay, so let's look. So based on the video that you watched just now, okay, which is in part 2, why do you really need the Fourier analysis? So the essential Fourier analysis is to represent signal in terms of complex exponential, or we call it as trigonometric function. So you see that just now we have the complex value j. So let's say that we have a signal xt. Okay, so you may write xt in terms of a combination of linear equation. So you have here sum of ak e j omega t equivalent to plus a minus e j omega t plus a minus plus a naught plus a1 plus a2 until infinity. So reason is that here is almost any signal can be represented as a series of complex exponential, which is what you saw in the video in part 2. And here is that response of an LTI system to a complex exponential is also a complex exponential with scale magnitude. So you can actually, in later on in Fourier series, is that you're going to actually plot the magnitude and the phase value using the Fourier series. And this is actually a compact way of approximating signals. So as you may see in the video, in part 2 is that, for example, you have a square wave signal. So you actually can approximate that square wave signal by using few sinusoidal or cosine wave signal. So by using this type of equation. So another reason why is that you may also store analog signal such as music in digital environment. So when you have this signal, so you can actually store it in digital environment, and over a digital network, it may be easier to transmit digital equivalent of signal instead of original analog signal. Okay, so let's just see here what are the representation of Fourier series. So Fourier series represent signals in terms of sinusoids. So which means that it's either in sine wave or cosine wave. So which leads to a new representation for signal as filters. Okay, represent signal by their harmonic components. So you may have the first harmonic, or second harmonic, third harmonic. So what does it mean by that harmonics? Okay, so a harmonic of wave is a component of frequency of the signal that is an integer multiple of the fundamental frequency. So let's say that, okay, you have only a periodic signal. Okay, all harmonic of omega naught are periodic in terms of t equal to 2 pi over omega naught. So here is that omega naught is the fundamental frequency and t is the fundamental period. So therefore, if you talk about a wave of a harmonic of wave, means that the integer multiple, so means that you have 2 pi over omega naught, 4 pi over omega naught, 3 pi over omega naught, and so on. So you actually multiply the integer part of the fundamental frequency. Okay, so this one is just how to actually calculate the fundamental frequency and fundamental period. This one I already explained in chapter 2 before. So let's say that you have this signal. If it starts from here, means that this is sine wave signal. Okay, so if it's being shifted like this, so this one will be a cosine signal. Okay, so means that you see here is that first original this signal is a sine 2 pi ft. If we have the phase here shift, then you have x plus pi over 2. Means that is being shifted by pi over 2. So how to calculate for fundamental frequency is this equation, and how to calculate for the fundamental period is this equation. So T naught will be in second, omega will be radian per second, and frequency will be 1 over second, which is hertz. Okay, let's see an example. Okay, example, we were talking about representing of signals by their harmonic component. So let's say that we have the omega naught, which is phantom frequency. So we call this as a harmonics. Okay, so it means that the first value here at 0 will be, at harmonic 0 will be the DC. Okay, DC value. Okay, and then we have the fundamental, which is omega naught, will be this value, fundamental frequency. Then we have the second harmonic, 2 omega naught, third harmonic, 3 omega naught, fourth harmonic, 4 omega naught, and so on. Okay, so this one can go up to infinity. So example of musical instruments. So let's say we were talking about just now, so each signal have their own waveform. So harmonic contents is natural way to describe some kinds of signals. So example, we have a signal for piano, it's like this, from cello, basin, horn, alto sax, and a violin. Okay, so let's say that by using Fourier series, you're going to plot the harmonics. Okay, calculate using Fourier series, then you can plot the harmonics. So this slide will show you the representative of the harmonics for each waveform for piano. It means that, let's say you have the piano here, so this represent the harmonics for the piano. You have the DC term, you have the fundamental frequency, you have the first harmonic, second harmonic, and so on. So for violin is indicated by this Fourier series, and for basson is indicated by this Fourier series. Okay, so this is just a recap from chapter 2. You were talking about how you can actually add, when you add some signal, a few signal, then you will get a larger waveform like this. So this one I already talked in chapter 2. So we have one first signal, second signal, third signal, fourth, fifth, and sixth. If you you use linearity, means that you combine all of this signal, you may actually get this signal. So I actually use the example of tsunami. Tsunami means that the first one, this first waveform will be the first signal. Then you have the second wave, third wave, fourth wave, fifth wave, and so on. So when you combine all with this wave, you may get the final waveform, which is a large tsunami. So actually, each of these small waveform is represented by their own frequency. Okay, so fundamental frequency. So for example, is that for this signal is by 6 omega naught. For this second signal is represented by 5 omega naught. And for the third signal is represented by 4 omega naught, so and so on. So if you were to actually have the result of the final waveform as below here, means that the Fourier series representative of this waveform is indicated by this Fourier sum of harmonics component. Okay, so means that you may see that actually a few waveform indication here. It means that you have the DC term, you have the first harmonic, second harmonic, and so on. Let's do an example. Let's see an example of using MATLAB. Okay, example is frequency domain representative of a discrete time signal. So even though we are discussing about continuous time signal, but let's say that I'm going to give you an example of a discrete time signal. So let's assume that we have a plot of a frequency f naught instead of omega naught. So in this term is that we're going to plot with respect to f naught. Normally we are going to, for Fourier series is that we are going to plot it using omega naught. But anyway, you know that omega naught is 2 pi f. So therefore you can actually just calculate what is omega naught. Okay, let's see an example is for this. We are using x1n equal to sine 2 pi f naught and ts. So means that we have omega naught t here. Okay, so when you plot that is that when we use the Fourier series representative, we will actually find out what is the fundamental frequency or omega naught. So fundamental frequency here, we say, let's say it's at f naught, and we have no amplitude of 1. So this is where you put f naught equal to 1. Okay. Let's look at another signal, which is x2n. So x2n is given by 0.4, the amplitude is 0.4. And then we have the frequency at 2 pi f. So f naught here is given by 2f naught. So 2f naught is the second harmonic. So let's say that we have the second harmonic at 2f naught, and we have the amplitude at 0.4. Okay. Therefore, if we are using the linearity function, okay, function property. So assuming that we have x1 plus x2 and like this, so we can actually write it out again as this equation. So therefore, when we combine these two signal, imagine that you have two waveform, like a ocean wave. So two different waveform, combine it, then we combine it like this by actually adding it up. Then you will have the property or the coefficient for the Fourier series as for f naught is 1 and f2 f naught is at 0.4. Okay, so of course when you draw out again this signal does actually is just to show you how to plot x1 and x2, but actually when you combine these two signals is you will have this type of waveform. Okay, so imagine that if you add more signal here, then add more signal, then it will become a larger waveform. Okay, so let's do the summary here. So harmonically related complex exponential. So means that first one is just now is on the linear combination. You can either add signal, you can add a scaling factor, okay, scaling property, or you can time shift the property. Means that in chapter 1 you actually learn about time scaling, okay, time shifting, okay, time reversal and so on. Okay. Second one is that we are going to use the linear combination of basic periodic signal. So we have xt equal to ej omega t, and then ej omega t is actually the sine wave sine function plus the cosine function in complex number. Okay, so given here that xt, we have the fundamental frequency omega naught and the fundamental period t naught is equal to 2 pi omega naught. So by having that is that we can actually write out the equation related to the complex exponential as ejk omega t equal to ejk k omega naught is substitute this value, then we have 2 pi over t. So k is the harmonic function which is at 0, plus minus 1, plus minus 2 and so on until infinity. Okay. So which means that the value k here is the fundamental frequency multiplied of omega naught. So we have 2, 3, 4 and so on to infinity. Okay, so in general for Fourier series that we are going to use commonly a periodic signal, means that a signal that is periodic. A periodic signal we are going to learn that in Fourier transform later on. So a periodic signal can be defined as a weighted sum of complex exponential. This summation is called Fourier series. So you can write the equation of Fourier series as is equation 1. So this one, please memorize it. Okay, this one you are going to refer it in this chapter. So xt is equal to summation of ak ejk omega t. Okay, or if you want to substitute omega, then you can use 2 pi over t. So what is omega? Omega is the fundamental frequency, t is fundamental period, and ak is the Fourier coefficient. So what we are going to learn is how to actually calculate for ak value at a certain frequency. So similar to what you have learned in chapter 2, which is convolution sum and convolution integral, you have the method or approach to use. So you have the SOP. So first one is that the Fourier series coefficient AK is defined as the equation AK here. So imagine that you have this equation xt is given by AK blah blah blah. So what you need to find out is what is value of AK. So AK is given by this equation. So this is equation number 2 that you need to memorize. So AK is equivalent to 1 over T. Differentiate it, integrate it from 0 to T. Kx T E minus JK omega T dt. So if you see here is that you have actually the component of xt inside here. Okay, so xt from integrated from the value 0 until t. Okay, so or this one will be equivalent to same thing, just substitute omega with 2 pi over t. So here is what it means that k, when k equal to 0, then k is this value here. So you have when k equal to 0, you get the a0, which is a constant value. So which is this one is normally known as the DC term. So at a0 is normally DC term. You do not have any complex value. You have only a constant value. So for k equal to plus minus 1, then you have at a1 and a minus 1. Okay, and this is both referred to as the fundamental component, or we call it as the first harmonic component. And for k, next you'll for k at plus minus 2, so you have substitute k here, so you have a2 and a minus 2. This one is referred to as the second harmonics. Okay, and in general, okay, so if you add this one, k equal to 3, k equal to 4, and so on, then you can actually get the value for the coefficient series, Fourier series coefficient ak, or you an and a minus n, which is this one referred to the nth harmonic component. So which means that what you're going to actually calculate, okay, imagine that you're given this signal. Okay, you do not know what type of signal is inside here. Are they 2 sine wave or 3 sine wave inside this signal? So you need to find out what is the value, the coefficient value ak. So you know that from doing these two combination of x1 and x2, you find out that you have actually two, you have first harmonic and second harmonic. So this is what it means, finding what is a1 and a2. Okay, so given this signal, find what is a1 and a2. So a1 and a2. Okay, so we were here just now. Okay, so how to find the coefficient ak when you are given continuous time predict signal xt? So you are given xt, find what is ak. So the method is that first determine the period of xt. So what is the period t of xt? Then second is find the fundamental frequency omega equal to 2 pi over t. And finally, evaluate the coefficient by using this formula, general formula. So ak equal to 1 over t from 0 until t, xt e minus k omega t dt. Okay. So this integration is actually represent the integration over any interval of length t. Okay, so later on we will see an example. So after calculating what is the value for ak, next step is actually plotting the magnitude of the Fourier series coefficient ak, okay, against the frequency, and also plotting the phase of the Fourier coefficient ak phase against frequency, yield the phase spectrum analysis. So just imagine like this. When you have a question on Fourier series is normally they will ask to find what is the Fourier series coefficient. Okay, find what is a k value up until k equal to 10. So find what is the value ak1, ak2 until ak10, or if you have the minus negative value, then ak plus minus 1, ak plus minus 2, and so on. Then from there, you will have both for value for ak, you will have the magnitude and the phase value. So from there is that you're going to plot for magnitude, okay, ak, and for the phase value ak.